picture a dimly lit control room. This is right at the heart of the United Kingdom's national grid,
Right.
and it's the evening of April 5, 2001. You've got this room full of highly trained electrical engineers, right? And they are just staring intensely at a bank of glowing monitors.
Which you'd expect. I mean, that's their job.
Exactly, but they aren't just looking at, like, voltage readouts or frequency charts. They're literally watching the BBC.
Yeah, they're watching an episode of the soap opera EastEnders.
Right. Specifically, they're waiting for the exact second a character named Lisa Shaw confesses to shooting Phil Mitchell.
It's just such a bizarre mental image.
It really is. Because the moment those credits roll, those engineers know that something like 22 million Britons are going to stand up, walk to their kitchens, and turn on their electric kettles for a cup of tea.
And that collective, synchronized craving for tea, it creates this instantaneous, just violent vacuum of power on the national grid.
Yeah.
We're talking about a demand spike of 2,290 megawatts hitting the system in a matter of, 2 to 3 minutes.
That's a staggering amount of power.
It is. And if the engineers in that room miscalculate the timing, even by a little bit, the frequency of the entire UK grid drops, safety relays trip, and parts of the country literally go dark.
It's the ultimate high-wire act, honestly.
Absolutely.
And it perfectly encapsulates the invisible, just incredibly precarious reality of the electrical infrastructure that keeps our modern world alive. So, welcome to the Deep Dive.
Glad to be here.
Today, you and I are going on a mission into the murky, wild, and sometimes really bizarre universe of energy storage.
We are definitely moving far beyond the standard lithium-ion battery in your phone, or your electric vehicle.
Right, way beyond that.
Yeah.
Our foundation today is this fascinating stack of research we're pulling from academic journals like Sustainability and Advances in Battery Technology.
Some really dense stuff in there.
Oh, extremely dense. Plus project profiles from IE Spectrum and detailed documentaries like Novia. We're extracting the most critical insights to bring you to the absolute bleeding edge of how humanity is trying to capture and store power.
Because the stakes here, they really couldn't be higher. The engineering choices we make over the next decade regarding bulk energy storage, they'll fundamentally hardwire the architecture of human society for the next century.
No pressure, right? To guide us through this landscape, I want to introduce a concept we found buried in one of the university electrical engineering syllabi we were reviewing.
I love this part.
It's an unofficial motto among researchers, and it sets the perfect tone for this whole exploration. It goes, electrical engineering is where almost anything can be a battery if you use it wrong enough.
It sounds like a total joke, but scientifically, it's a profound truth.
How so? To a layperson, a battery is a very specific thing.
Right. The general public has been conditioned to think of a battery as a discrete, manufactured object, like a AA cylinder or a sleek rectangular lithium-ion pack.
Yeah, a physical object you buy at the store.
Exactly. But functionally, in physics, a battery is simply an energy conversion mechanism. That's it. It takes energy from one state, holds it in a stable form, and returns it on demand.
So the form factor doesn't matter at all.
Not even a little bit. Whether that energy is held in a chemical bond, thermal mass, or kinetic motion, a battery is just captured potential.
Which requires us to completely unlearn all our assumptions. So let's start with why we even need to unlearn them. Why are we desperately looking past lithium-ion in the first place?
Well, it's a good question because lithium-ion is arguably one of the greatest engineering triumphs of the last 50 years.
Right. It hits this incredible sweet spot of high energy density, meaning it packs a massive amount of power into a very lightweight, compact footprint.
Which is why it revolutionized portable electronics and EVs.
And the economics have scaled brilliantly, haven't they? The IE Spectrum data we reviewed notes that in 2013, lithium-ion cost roughly $568 per kilowatt hour.
Yeah, and by 2025, that cost had plummeted to around $74 per kilowatt hour.
That is a total revolution. So why abandon a winning horse? If it's getting that cheap, why not just build more of them?
Well, we aren't abandoning it, but we are acknowledging its physical and, frankly, its economic ceiling.
Okay, what do you mean by ceiling?
Lithium-ion is optimized for a very specific application, right? Delivering high power in a constrained mobile footprint. It's a sprinter.
Sprinter, right.
But the grid requires a vastly different biological profile, so to speak. When you attempt to scale lithium-ion to the utility level, like building massive fields of shipping containers filled with these cells, the economics start to break down at around the 4 to 6 hour mark of continuous storage.
Wait, really? So an array the size of a football field gives you maybe 6 hours of backup?
At an economical price point, yes. That gets a city through the evening peak when the sun sets on the solar panels and everyone turns on their air conditioning, but that's about it.
That feels incredibly limiting.
It is. And beyond the duration limit, you have the physical degradation of the chemistry itself.
Like how my smartphone battery won't hold a charge after a couple of years.
Exactly like that. That's because lithium-ion cells suffer from inherent capacity fading. Every time you cycle the battery, parasitic chemical reactions consume a tiny fraction of the active lithium.
So it's basically eating itself.
Kind of, yeah. There's also the degradation of the solid electrolyte interface, or the SEI.
Let's pause on that because the SEI layer is critical to understand if we're looking at chemical alternatives later.
Yeah.
The SEI is basically a protective crust, right? That forms on the anode during the battery's first few charge cycles.
Spot on. It's a passivation layer. It is absolutely necessary to stop the liquid electrolyte from continuously reacting with the carbon anode.
Okay, so it protects the battery. That sounds like a good thing.
It is, but here's the fatal flaw. As the battery charges and discharges, the anode physically expands and contracts.
Like it's breathing.
Yeah, a mechanical swelling. And this mechanical stress causes that protective SEI layer to crack. Oh, I see.
So when it cracks, the battery then has to consume more active lithium and electrolyte to basically heal the crack and form new SEI.
So over thousands of cycles, what happens?
The SEI layer grows thicker and thicker, which increases the internal resistance of the cell, and it permanently depletes the lithium inventory. The battery essentially suffocates itself over time.
Wow. Combine that internal degradation with the thermal instability. I mean, these batteries generate intense heat that requires active, energy-intensive cooling systems,
Right, you have to run air conditioning just to keep the batteries from catching fire.
which drains the battery you're trying to save.
Yeah.
You realize lithium-ion is just far too fragile to be the sole backbone of a national grid, especially when you confront the meteorological reality of renewable energy.
Oh, absolutely. The weather doesn't care about our battery limits.
Exactly. Which brings us to this brilliant piece of terminology we found from the German grid engineers, the Dunkelflaut.
I love that word. It translates directly to dark doldrums. Right. And a Dunkelflaut isn't just, a cloudy Tuesday afternoon.
Yeah.
It is a specific multi-day meteorological phenomena.
It's the nightmare scenario for renewable grids.
It really is. A massive high-pressure system settles over a region during the winter, bringing stagnant windless air accompanied by thick, low-lying cloud cover.
So you are staring at zero wind generation and near zero solar generation simultaneously for days on end.
And this usually coincides with freezing temperatures, right? Meaning heating demand is at its absolute peak.
Yeah, everyone is turning on their electric heaters while the wind turbines are standing completely still.
So put yourself in the shoes of a grid operator. You are trying to keep Chicago or Berlin from freezing for 4 straight days of a Dunkelflaut, and your only backup is a lithium-ion array that drains to zero in 4 hours.
The math is just terrifying.
It makes it glaringly obvious that we need massive, slow-release bulk storage. We don't just need sprinters, we need marathon runners.
But, and here's why grid engineering is so difficult, the grid is uniquely paradoxical. We need those multi-day marathon runners, yes, but we still have to manage the fact that electricity is the ultimate perishable commodity.
Meaning it has to be used the exact second it's generated.
Exactly. In an alternating current grid, generation and consumption must be perfectly matched at a fraction of a second. If demand suddenly outstrips supply, the frequency of the grid, which sits at 60 hertz in North America and 50 hertz in much of the rest of the world, begins to physically slow down.
Which loops us right back to that control room in the UK on April 5, 2001. The Great British Kettle Surge.
The technical term for this in grid dynamics is TV pickup.
TV pickup. It is a fascinating sociological anomaly that creates an absolute engineering nightmare.
Well, and it's uniquely British because of their appliances, right? The UK operates on a 230-volt system, which allows their electric kettles to draw significantly more power than American models.
Right, they boil water way faster.
Yeah, typically around 2.5 to 3 kilowatts per kettle. That's a massive power draw for a single countertop appliance.
I was trying to conceptualize this, and the closest parallel I can think of is centralized water pressure.
Okay, how so?
Imagine a massive, city-wide water tower. If every single person in the city opens every faucet in their house to full blast at the exact same millisecond, the pressure in the entire municipal system drops to a trickle instantly.
That's a great analogy.
That is what millions of 3-kilowatt kettles do to the electrical frequency of the grid. It's just a sudden, violent drop in pressure.
And the grid operators literally watch television to prepare for it. The data in the sources maps out the historical surges, and it's wild.
What are some of the biggest ones?
Well, a standard episode of EastEnders generates a TV pickup of roughly 200 to 800 megawatts.
Just on a regular Tuesday.
Yeah. But special events are way worse. The end of the 1990 World Cup semifinal between England and West Germany caused a massive spike.
Because everyone held it in during the game and then went to make tea when it ended.
Exactly. The 1999 solar eclipse caused an enormous surge, too, when millions of people simultaneously went back inside and turned their industrial machinery and computers back on.
But that 2001 EastEnders episode still holds the record, right?
It does, a legendary peak of 2,290 megawatts.
So how do you actually handle that? How do you inject 2,290 megawatts into the grid in under 3 minutes to stop the frequency from collapsing? I mean, you can't just throw more coal into a furnace.
No, absolutely not. A thermal power plant takes hours, sometimes days, to fully spin up its steam turbines.
Right.
You need an ultra-fast response battery. And the weapon the UK utilizes is pumped hydro storage. Specifically, this marvel of engineering in Wales called Dinerwig, known affectionately as Electric Mountain.
Built inside an abandoned slate quarry, right?
Right. They literally hollowed out the mountain and built a massive reservoir high above a lower lake.
So it's just a giant pool of water sitting at the top of a mountain.
Exactly. When the engineers in the control room see the credits roll on the television, they remotely open these massive hydraulic valves inside Electric Mountain. Millions of gallons of water drop through 16-foot wide tunnels carved into the solid rock, hitting giant reversible pump turbines.
And how fast does that actually generate power?
Dinerwig can go from zero output to injecting 1,320 megawatts of power into the grid in just 12 seconds.
12 seconds. It is a literal mountain functioning as a high-speed emergency battery.
It's incredible. They use that alongside drawing immediate power through undersea high-voltage direct current cables connected to France to bridge the 3-minute gap until the kettles boil and turn off.
It perfectly illustrates the dichotomy of grid storage. We require an incredibly diverse portfolio.
Yes, we do.
We need the lightning-fast 12-second response of Electric Mountain for sudden surges, and we need entirely new technologies to survive the week-long dark doldrums.
Exactly. The sprinters and the marathon runners.
So let's dig into those new marathon runners. If lithium is too expensive and chemically fragile for utility-scale bulk storage, the research journals point us toward the rest of the periodic table.
And it turns out the answers might be incredibly cheap and incredibly salty.
Right. I was diving into the Advances in Battery Technologies papers on sodium-ion batteries, and it feels like such an obvious solution. Why not use sodium, which is infinitely abundant in ocean water and table salt, instead of rare, geopolitical, bottlenecked lithium?
Well, from a purely chemical standpoint, they operate on the exact same fundamental principles. If you look at the periodic table, sodium sits directly below lithium in group 1, the alkali metals.
Well, they have similar traits.
Very similar. They both have a single electron in their outermost shell that they are very eager to shed. And that shedding of an electron is the core mechanism of electrical current.
So if they behave the same way chemically, why have we spent 40 years commercializing lithium while sodium just sat on the shelf?
It basically comes down to subatomic real estate.
Real estate.
Yeah. While they share chemical behaviors, a sodium ion is physically much larger than a lithium ion. A lithium ion has a radius of about 90 picometers. A sodium ion is roughly 116 picometers.
Which sounds microscopic, but at the atomic level, that's a massive volumetric difference. It's like, what, a 30% increase in size?
Exactly. It's a catastrophic increase in size when you consider how a battery actually stores these ions.
Okay, walk me through that.
When a battery charges, the ions are pushed out of the cathode, they travel through the liquid electrolyte, and they force their way into the crystalline structure of the anode. This process is called intercalation.
Intercalation.
Rasp.
Right, so they have to park themselves inside the host material.
Precisely. Now, standard lithium-ion batteries use graphite for the anode. Graphite consists of neatly stacked, flat sheets of graphene.
Like pages in a book.
Yes. The van der Waals forces holding those sheets together create a very specific gap size. Lithium ions slip into those gaps perfectly.
But sodium is too big.
Right. When you try to force a bulky sodium ion into standard graphite, it's like trying to parallel park an 18-wheeler in a compact car space.
It's just not going to fit.
No, and the sodium ions cause massive volumetric expansion, literally shredding the graphite layers and destroying the battery structure. Sodium just has terrible intercalation kinetics in standard materials.
But the recent breakthrough detailed in the MIT Technology Review and Sustainability journals shows they bypassed the graphite problem entirely, right? By synthesizing a new architecture.
Yes, and it's brilliant. Instead of neatly stacked graphite sheets, they use something called hard carbon.
What exactly is hard carbon?
Hard carbon is a highly disordered amorphous carbon structure. Instead of looking like neatly stacked sheets of paper, its atomic structure looks more like a randomly assembled house of cards.
Oh, interesting. So it's messy.
Very messy. It has wide pores, vast empty voids, and chaotic gaps. This disorganized structure provides ample room for the bulky sodium ions to intercalate and extract quickly without causing physical strain on the material.
So they basically built a bigger parking garage for the bigger ions.
That's exactly what they did.
And on the other side of the battery, the cathode, the materials are wildly cheap. I mean, they aren't relying on cobalt from the DRC or nickel from Indonesia.
No, they're using things we already produce in massive quantities.
Right. One of the primary cathode materials being tested for sodium ion is actually a derivative of Prussian blue.
Yes, the exact same synthetic pigment used for centuries in blue jeans and traditional architectural blueprints.
I couldn't believe that when I read it. Blue jeans, pigment in a grid battery.
It's wild, but it makes structural sense. At an atomic level, Prussian blue has a face-centered cubic lattice framework. It is essentially a rigid 3D grid with wide open channels running through it.
Like a microscopic scaffolding.
Exactly. Those channels act like superhighways, perfectly sized for sodium ions to flow through with minimal resistance.
And the commercialization is happening incredibly fast, too. The sources note that CATL, which is the largest battery manufacturer on Earth, has pushed sodium-ion energy density to 175 watt-hours per kilogram.
Which is getting very competitive with low-end lithium cells.
Yeah. We are already seeing major electric two-wheeler companies like Yadia rolling out sodium-ion scooters. The capital cost projections are hovering around $40 per kilowatt hour, which is nearly half the cost of tomorrow's cheapest lithium cells.
And for grid applications, weight doesn't matter anyway. A grid battery just sits in a field.
It doesn't need to fit in a pocket or fly an airplane.
Exactly. A company called Inlight Energy recently completed successful testing in the UK of a grid-scale iron sodium metal chloride battery. It's a literal salt battery.
And how did it perform?
It achieved an 83% round-trip efficiency without a single gram of lithium, cobalt, or nickel.
That is huge. Okay, if salt batteries blew my mind, the next chemical alternative feels like science fiction disguised as, well, rust.
Oh, the Form Energy Iron Air battery.
Yes. I was reading the NoVA profile on Form Energy's iron air battery, and the mechanism here fundamentally changes how we think about energy duration.
It really does.
Walk me through this, because normally oxidation and rusting are the absolute enemy of structural and electrical engineering. You want to avoid rust at all costs.
Right. In traditional engineering, rust is decay. It's failure. But Form Energy recognized that the chemical process of oxidation is fundamentally just a transfer of electrons from the metal to the oxygen.
Yeah.
And if you can capture and reverse that transfer, you have a battery. They engineered a system based on reversible rusting.
Reversible rusting. The battery actually breathes, doesn't it?
Literally breathes. During the discharge phase, when the grid needs power, the battery opens valves and inhales ambient oxygen from the air.
It's regular air from outside.
Yep. That oxygen reacts with thousands of tiny iron pellets inside the battery cells, converting the metallic iron into iron oxide, rust.
Okay, so it rusts on purpose.
Exactly. As those chemical bonds form, the iron sheds electrons, which are harvested and sent out to the grid as electrical current.
So the battery is purposely destroying its own iron core to generate electricity.
That's one way to look at it, yeah.
But I have to push back here on the thermodynamics, because rusting is an exothermic reaction, right? It releases heat.
Yes, it does.
And reversing that, stripping the oxygen away from the iron to unrust it, that requires a massive input of energy to break those chemical bonds.
Mm-hmm.
Aren't you taking a severe thermodynamic penalty on the round-trip efficiency?
You are absolutely taking a penalty. The round-trip efficiency of an iron-air battery is only about 50%.
50%. So you are losing half the energy you put into it, primarily as heat.
Right. If you compare that to a lithium-ion battery, which boasts a 95% round-trip efficiency, iron-air looks terrible on paper
So why on earth are grid operators rushing to buy them?
because of the capital cost and the duration. Iron, water, and air are three of the cheapest, safest, and most abundant resources on the planet.
So the materials cost is effectively zero compared to refined lithium.
Exactly. And Form Energy System is designed to provide 100 hours of continuous power delivery.
100 hours.
Yes. That is 4 full days, enough to survive the worst of the German Dunkelflaut we talked about, and they're delivering this at roughly 1/10 the capital cost of a lithium-ion equivalent.
Wow, 1/10 the cost.
Yeah. When you are buying massive bulk storage for extreme weather events, you don't care about a 50% efficiency loss on cheap solar power. You care about the total capital expenditure to keep the lights on for 4 days.
That makes perfect sense. And honestly, the human narrative surrounding the manufacturing of these batteries is just as compelling as the chemistry.
The factory location, right?
Yes, Form Energy isn't building these high-tech modules in a pristine Silicon Valley lab. They chose to build their primary $750 million manufacturing facility in Weirton, West Virginia.
A town historically defined by the American steel industry.
Defined by it and entirely devastated by its loss. In 1909, Ernest Weir built a massive steel mill there that eventually employed over 10,000 people.
It was huge.
It was the generational lifeblood of the entire region. But international competition and market shifts led Weirton Steel into bankruptcy in 2003. The mills were largely demolished. It became a textbook symbol of the Rust Belt's decline.
And now they're literally building a rust battery factory on the ashes of that old steel mill.
It's incredible economic poetry, isn't it? They are leveraging the deep generational knowledge of the local workforce in handling heavy iron.
Because they already know how to work with the material.
Exactly. They are utilizing the existing river barges and heavy rail infrastructure originally built for steel exports. It proves that the transition to next-generation energy doesn't require abandoning the communities that built the infrastructure of the 20th century. You can adapt them.
It is a profound shift. We are moving from manipulating rare elements to manipulating the most common elements on Earth. But, chemistry is only one half of the battery universe.
Right. Our motto says anything.
Exactly. If we want to truly grasp the unofficial motto that anything can be a battery, we have to look at pure brute force physics.
Mechanical energy storage. No chemical bonds, no electrolyte fluids, just physics.
The purest form of storage.
Well, let's start with kinetic energy, and specifically flywheels. A flywheel is essentially a very heavy rotor suspended in a vacuum, spun up to extreme speeds.
It's a beautifully simple concept.
To visualize this, think of an Olympic figure skater. When they start a spin with their arms outstretched, they rotate at a moderate speed. But the moment they pull their arms in tight against their body, their rotational velocity explodes.
They are conserving angular momentum.
Right. And the underlying physics is defined by the rotational kinetic energy equation, isn't it?
Yes. Energy equals 1/2 times the moment of inertia times the angular velocity squared. E equals 1/2 I omega squared.
I know we promised to avoid dense math, but that squared function on the velocity, that's the whole secret to flywheel engineering, isn't it?
It dictates the entire design philosophy. Because velocity is squared in the equation, if you simply double the mass of your flywheel, you only double your stored energy.
Okay, a linear increase.
But if you double the speed at which it spins, you quadruple the stored energy. Therefore, modern mechanical engineers are not trying to build the heaviest steel wheels. They are trying to build incredibly lightweight wheels that can survive rotating at terrifying speeds without succumbing to centrifugal disintegration.
Because a standard steel block would just, tear itself apart into shrapnel at those speeds?
Exactly. The tensile strength of steel just isn't high enough. This is why cutting-edge flywheels, like the NASA G2 system developed for spacecraft, use advanced carbon fiber composite rotors on titanium hubs.
The sources state the NASA G2 spins at 60,000 revolutions per minute. 60,000 RPM.
It's almost unfathomable.
A car engine redlines at maybe 7,000 RPM.
Yeah.
How do you even manage the friction of an axle spinning 1,000 times a second? Traditional ball bearings would melt in seconds.
You eliminate mechanical contact entirely. The rotor is placed inside a hard vacuum chamber to eliminate aerodynamic drag.
Okay, so no air friction.
Right. Then, the entire massive spinning cylinder is levitated using magnetic bearings.
Wait, so it's floating in a vacuum, touching absolutely nothing.
Touching nothing. Though, it's worth noting, magnetic bearings aren't a perfect silver bullet. Active magnetic bearings require a constant feed of electricity to power the electromagnets that keep the rotor centered.
Which creates a parasitic drain on the battery's efficiency.
Right. Some experimental designs use high-temperature superconducting bearings that require liquid nitrogen cooling to achieve passive levitation. But the result is a friction-free environment where the rotor can spin for days with minimal energy loss.
And because it's purely mechanical, a flywheel doesn't have the chemical lag of a lithium battery. It can dump its entire energy reserve into the grid instantaneously.
The ultimate sprinter.
Exactly. The IE spectrum profile mentions that modern aircraft carriers use massive flywheel banks in their electromagnetic aircraft launch systems, or EMALS.
Oh, that's a perfect application.
Right, because the ship's nuclear reactor provides a steady flow of baseline power, but it can't deliver the instantaneous mega spike needed to catapult a fighter jet off the deck.
So they use the flywheels as a buffer.
Exactly. The reactor slowly spins up the flywheels over a minute, and then the flywheels dump all that kinetic energy into the linear induction catapult in 2 seconds.
It's brilliant, but there is a phenomenal, almost mind-bending nuance to flywheel physics that the research journals brought up. It involves planetary mechanics.
Planetary mechanics from a spinning wheel.
Yes. When you have a massive, dense object spinning at 60,000 RPM, it acts as a highly rigid gyroscope. It wants to maintain its exact orientation in absolute space.
Right, gyroscopic stability. Like a toy top.
But the Earth is rotating beneath it. Because the flywheel rigidly holds its orientation while the planet turns, the Earth's rotation actually exerts a twisting force against the levitating magnetic bearings.
Wait, really?
Yeah, it's an iteration of the Foucault pendulum effect. Over time, this planetary gyroscopic friction actually drains the kinetic energy out of the flywheel.
That is insane. So how do they fix it?
To achieve maximum efficiency, engineers have to precisely align the axis of the flywheel rotor, so it sits perfectly parallel to the Earth's axis of rotation.
We have to align our terrestrial batteries with the tilt of the planet to stop the Earth's rotation from stealing our stored electricity.
It's just incredible.
That is easily one of the most stunning engineering constraints I ever heard.
Physics doesn't let you cut corners.
Clearly not.
Oh.
Okay, let's move from kinetic energy to gravitational energy. Mass times gravity times height. E equals MEHE.
Pumped hydro.
Right. We've already discussed the pumped hydro system at Electric Mountain. The sources also highlight the Ludington plant in Michigan, which holds 27 billion gallons of water and acts as a massive peaker plant replacement.
But pumped hydro has a fatal flaw, doesn't it?
Geography. We are rapidly running out of suitable mountains to hollow out, and flooding vast valleys carries enormous ecological consequences.
Which is why the engineering community is looking downward. We can't easily build new mountains, but we already have millions of massive pre-excavated voids deep underground.
The legacy of the 19th and 20th century fossil fuel booms.
Exactly. There are an estimated 500,000 abandoned coal and hard rock mines in the United States alone. In China, as they transition their energy economy, projections suggest they will have 15,000 abandoned deep mine shafts by 2030.
And the proposal is to turn these legacy holes into closed-loop underground water batteries.
That's an elegant solution.
The pilot project detailed in the journals is the Prosper Haniel hard coal mine in Germany. The geometry is staggering. It has horizontal galleries stretching 25 kilometers, and the main vertical shafts plunge 1.2 kilometers straight down into the earth.
1.2 kilometers down, that's massive.
It has a volumetric capacity of 1 million cubic meters.
So the mechanics are elegantly simple. You build a reservoir on the surface. During off-peak hours, when wind power is practically free, you pump the water from the deep mine up to the surface.
And then when you need the power back.
When demand peaks, you open the valves, and the water falls 1.2 kilometers straight down the shaft through a massive hydroelectric turbine.
But let me test that assumption, because any environmental scientist will tell you that abandoned coal mines are a chemical nightmare.
Acid mine drainage.
Right. When the iron sulfide pyrite in the coal seams is exposed to oxygen and water, it oxidizes to form sulfuric acid. The water at the bottom of these mines is highly acidic and laden with dissolved heavy metals.
It's incredibly toxic.
So if you take millions of gallons of toxic, highly corrosive sulfuric acid water, and forcefully cycle it up and down through millions of dollars of precision steel turbines every single day, won't the entire system just dissolve?
It is the primary engineering bottleneck, yes. You've identified the exact problem being researched by scientists like Them Inglayan at the Oak Ridge National Laboratory.
Oh, so they're actively working on this.
Very actively, they are conducting aggressive tribological and hydrodynamic modeling on this. You cannot just use off-the-shelf hydro turbines. They require advanced anti-corrosive polymer coatings and specialized metallurgical alloys.
Because regular steel would just melt away?
Pretty much. But the chemical erosion is only half the threat. The other half is structural fatigue.
You mean the mine collapsing?
Exactly. The sedimentary rock walls of a coal mine were excavated a century ago to remain static. They were never designed to endure cyclical, pressurized inundation.
Meaning being filled and emptied over and over.
Right. When you rapidly fill a 1.2-kilometer shaft with water, you introduce immense hydrostatic pressure against the rock face. When you pump the water out, the pressure releases.
So squeezing and relaxing the rock every day.
Doing this daily forces the rock to physically expand and contract. Over thousands of cycles, the geological formations suffer mechanical fatigue. Oak Ridge is meticulously modeling the Young's modulus and tensile strength of these specific shale and sandstone layers to ensure we don't trigger localized seismic events or catastrophic shaft collapses.
Wow. So turning a coal mine into a battery is as much a geotechnical engineering challenge as it is an electrical one. This brings us perfectly to the next frontier. If we can store energy by spinning heavy objects, or by moving heavy objects up and down, what about changing the physical state of the material itself? Let's dive into thermodynamics.
Manipulating heat and pressure.
Yes. The fundamental principle of thermal storage is incredibly intuitive, isn't it? Heat is energy.
It's the most basic form of energy we interact with.
If you have a massive block of material that can absorb heat, retain it without degrading, and release it hours later, you have a battery.
And the most prominent commercial example of this is molten salt storage, primarily used alongside concentrated solar power arrays, or CSP.
Right, because instead of photovoltaic panels that convert photons directly into electrons, CSP uses vast fields of parabolic mirrors to concentrate sunlight onto a central receiver tower, generating blistering intense heat.
They use that thermal energy to melt a precise mixture of salts, usually sodium nitrate and potassium nitrate.
Just massive vats of liquid salt.
Yep. They pump this molten liquid salt into heavily insulated storage tanks. And the specific heat capacity of these salts is phenomenal.
How long can they actually hold the heat?
The sources confirm these two tank systems can retain temperatures exceeding 500 degrees Celsius for 6 to 15 hours with minimal thermal loss.
That easily covers the evening pick.
Exactly. When the grid needs power after sunset, the molten salt is pumped through a heat exchanger to boil water, generating high-pressure steam that drives a conventional turbine.
But you don't even need specialized chemical salts, do you? The journals highlight an experimental project in Finland using literal sand.
The sand battery. I love this one.
They built these massive insulated silos, filled them with hundreds of tons of crushed soapstone and low-grade builder's sand, and used excess wind energy to power resistive heating elements buried inside.
Like a giant toaster element.
Exactly like that. They heated the sand to 500 degrees Celsius. But they aren't turning it back into electricity, are they?
No, the efficiency loss would be too great to convert it back to electricity.
Right, so they used the stored heat directly, dispatching it into the municipal district heating network to warm homes during the Finnish winter.
It proves the motto perfectly. A silo of hot dirt is a highly effective battery if used correctly.
Hot dirt. I love it. And if we move from manipulating temperature to manipulating pressure, we encounter compressed air energy storage, or CAEs.
CAEs. This is an oldie but a goodie.
This isn't theoretical at all. The sources note CAE plants have been operating since the late 1970s in places like Huntorf, Germany.
Yeah, the concept is fairly straightforward. You take excess electricity, run giant air compressors, and force millions of cubic feet of air down into subterranean geological voids.
Typically salt dome caverns, right?
Yes. To get the energy back, you release the pressurized air to spin a turbine. But there is a massive thermodynamic catch here.
And anyone who has ever manually inflated a bicycle tire with a hand pump knows the physics of compression. When you compress a gas, it gets hot.
Very hot. The mechanical work of forcing gas molecules closer together generates significant thermal energy.
In the older legacy CES systems, which the engineers call diabatic systems, that heat of compression was treated as an annoying byproduct,
They literally vented the heat out of cooling towers into the atmosphere.
which is a catastrophic loss of the very energy you were trying to store. But the thermodynamic penalty hits you twice, doesn't it?
It hits you coming and going because you threw away the heat during compression. When you later open the valve to release the high-pressure air, the gas expands rapidly.
And rapid expansion means cooling.
Extreme cooling. According to the Joule-Thomson effect, rapid expansion causes a massive drop in temperature. The expanding air becomes so incredibly cold that it would physically freeze the lubricating oils and shatter the metal blades of the turbine.
So to prevent the turbines from freezing,
Mm-hmm.
those 1970s plants had to actively burn natural gas to heat the air back up before it hit the turbine.
Which is just, I mean, you are using a fossil fuel to discharge your renewable energy battery.
It completely defeats the purpose.
It really does. Which is why the industry has shifted entirely to adiabatic CES designs.
What's the difference there?
In an adiabatic system, the heat generated during the compression phase is captured by a thermal storage medium, often a massive insulated bed of crushed rock or thermal oil.
So they save the heat for later.
Exactly. Then, during the discharge phase, that exact same captured heat is reapplied to the expanding air. It eliminates the need for natural gas and drastically increases the round-trip efficiency of the cycle.
That's brilliant. But CAES still suffers from the pumped hydro problem, which is geography. If you don't happen to have a massive, airtight subterranean salt cavern in your backyard, you can't build a compressed air plant.
You're geologically restricted.
This leads us to one of the most elegant, mind-bending technologies we found in the literature. Liquid air energy storage, or LAEs.
Oh, this is cryogenic phase change engineering at its absolute finest.
The Novier piece and the engineering journals profile a facility built by Highview Power in Bury, near Manchester in the UK. They bypass the need for underground caverns entirely by pushing the compression to an extreme.
How
They use off-peak electricity to power massive industrial refrigeration cycles, compressing and chilling ambient air down to minus 196 degrees Celsius.
At minus 196 Celsius, the nitrogen and oxygen in the air drop below their boiling points. The gas undergoes a phase change and condenses into a cryogenic liquid.
And the volumetric math here is the magic. When air turns liquid, it shrinks by a factor of roughly 1,000.
1,000 times smaller.
Yes. You can take an entire warehouse full of air and condense it down to fit inside a single, above-ground, heavily insulated steel tank.
But again, I have to challenge the thermodynamics here. Chilling anything to minus 196 Celsius requires a massive input of compressor energy. Aren't you taking a huge efficiency hit on the front end?
You are. The physics demands a high energy price for liquefaction. But LAES claws back its efficiency during the discharge phase through integration with existing infrastructure.
How so?
When the grid demands power, that sub-zero liquid air is pumped at high pressure into an evaporator heat exchanger. It is exposed to normal ambient temperatures. But the genius of LAES is that you can expose it to industrial waste heat.
Oh, right. You build the liquid air plant next to a steel mill or a nuclear reactor or a massive data center that is desperately trying to vent heat.
Exactly. You funnel that waste heat into the liquid air. The cryogenic liquid instantly boils back into a gas, expanding 1,000 times in volume in a fraction of a second.
And that violent, massive volumetric expansion is directed through a turbine to generate electricity.
Yes, it is fully location-independent bulk storage. You don't need a mountain, you don't need a salt cavern, you just need a concrete pad and some insulated tanks.
And a nearby heat source, which we have plenty of.
Exactly.
Hmm.
Okay, let's take a breath and zoom out. We've explored the atomic strain of sodium ion, the thermodynamics of reversible rusting, levitating carbon flywheels fighting the Earth's rotation, hydrodynamic fatigue in abandoned mine shafts, and cryogenic liquid air.
We've covered a lot of ground.
We really have. And logically, as complex as these are, the underlying physics makes sense. But to truly embrace our guiding motto, that anything can be a battery if you use it wrong enough, we need to push into the absolute fringes of human ingenuity. We have to get weird.
The fringes are where the fundamental constraints of material science are tested.
I want to pose a thought experiment to you, the listener. It's something practically every middle schooler asks when they learn about electricity. Every single day, planet Earth is hit by approximately 8.6 million lightning strikes.
That's a lot of electricity.
Each one of those strikes carries about 1 billion joules of electrostatically stored energy. As the research points out, a single bolt of lightning contains enough energy to instantly boil 3,000 of those British tea kettles we talked about earlier.
So it's immense power.
With a near-infinite free supply of gigawatt-level energy literally raining down from the sky, why hasn't human engineering figured out how to just catch it? Put up a giant conductive tower, catch the lightning, and run a city for a week.
It is the ultimate mad scientist fantasy. It's Benjamin Franklin's Leyden jar scaled up to grid proportions.
Right. So why don't we do it?
Well, the physics of electrical discharge brutally shut down the dream.
Let's test the assumption. Why exactly does my skyscraper-sized lightning farm fail?
It fundamentally fails because of the duration of the event and the dielectric breakdown of storage mediums. A lightning strike carries immense, staggering power, often exceeding 100 gigawatts.
Okay, so plenty of power.
But the entire event lasts for mere microseconds.
A millionth of a second.
Yes. To physically capture that much energy that quickly, you cannot use a chemical battery.
Why not?
The intercalation kinetics we discussed earlier, ions moving through liquid to embed in carbon, are far too slow. If you hit a lithium or sodium battery with a 100 gigawatt spike, the internal resistance would cause the electrolyte to instantly vaporize, and the entire assembly would just explode into plasma.
Okay, so a lightning strike would basically turn a battery into a bomb. So chemical batteries are out. What about capacitors? They store electricity statically on plates, not chemically, right?
They do, but you would need a capacitor matrix roughly the size of a skyscraper to absorb that kind of voltage without dielectric breakdown.
What's dielectric breakdown?
It means the electricity would just arc right through the insulating material and destroy it. But even if you spent billions of dollars to build the skyscraper capacitor, the economics are atrocious.
Because of the capacity factor.
Precisely. You would be spending billions of dollars on a massive, highly dangerous piece of infrastructure that sits completely idle 99.999% of the time. Economically and mathematically, steady, boring solar panels and wind turbines make infinitely more sense.
So capturing lightning is a dead end. But I'm going to rebound with some other weird ones we found. What about nuclear batteries?
Oh, these are fascinating. Companies like Betavolt are working on these.
Right. Batteries that can last 50 years without a charge. It sounds like a sci-fi movie. How do they work?
They rely on the natural decay of radioactive isotopes, like carbon-14. As the isotope decays, it releases electrons. If you sandwich that between diamond semiconductor layers, you can harvest those electrons.
So it's constantly trickling out power for decades.
Exactly, but the power output is minuscule. We're talking microwatts. Enough for a pacemaker or a deep space sensor, but not a grid.
Still, a 50-year battery is incredible. And what about biological options? The sources mention biophotovoltaic cells using living cyanobacteria.
Yeah, green solar panels. They basically hijack the photosynthesis process. The bacteria absorb sunlight and water, and as they metabolize, they excrete electrons that we can harvest.
Or using the acid mine drainage we talked about earlier. There are bacteria that eat the heavy metals in the toxic water and produce a current.
It's true. Nature has been moving electrons around for billions of years. We're just finally trying to tap into it.
And we can tap into our own bodies, too. Thermoelectric generators capturing body heat to power medical devices, or piezoelectric shoe insoles that charge your electronics just by walking.
The piezoelectric effect is great. Certain crystals generate a voltage when you apply mechanical stress, like stepping on them.
It's like we're turning every possible action into a battery. Even origami. I saw the research on flexible, shape-shifting batteries from Linköping University that move like worms for soft robotics.
It just shows how versatile the concept of a battery really is.
Speaking of versatile concepts, I have to ask about the classic science fair project, the lemon battery, or the potato battery.
Yes. The great electrolyte misconception.
Right. Everyone assumes the lemon is providing the electricity.
It's not. The lemon is just the electrolyte. The energy actually comes from the chemical reaction between the two different metal electrodes you stick into the lemon, usually a zinc nail and a copper penny.
So the lemon isn't the battery, the metals are the battery.
Exactly. The acidic juice just allows the ions to flow.
Okay, so a lemon is a terrible battery. But I have another weird breakthrough from MIT and Harvard that sounds equally absurd, but the physics actually work. We are going to turn the very physical foundation of your house into a structural battery. Let's dig into supercapacitor cement.
This represents a total paradigm shift in how we view the built environment.
Concrete is the most consumed man-made material in the world, right?
By far. It is everywhere, but it is functionally inert. It just sits there holding things up.
Well, the researchers at MIT looked at the basic recipe for cement powder and water, and introduced a third highly specific ingredient, carbon black.
Which is fascinating from a historical perspective. Carbon black is an incredibly fine, highly conductive particulate resembling ultrapure soot.
Like fireplace soot.
Similar, but much more refined. It has been used as a pigment for millennia. It is actually the exact same material that was mixed into the ink used to write the Dead Sea Scrolls in the 3rd century BCE.
The idea that the ink of the Dead Sea Scrolls is the key to next-generation grid storage is just incredible.
Yeah.
How does it work mechanically within the cement?
The magic occurs during the hydration and curing process. When the cement is wet, the carbon black particles are dispersed throughout the slurry. As the cement cures and hardens, the water is slowly consumed by the chemical reaction or evaporates.
Leaving behind empty space.
Yes. As the water recedes, it leaves behind an intricate, microscopic, highly branched network of capillary tunnels inside the solid cement matrix.
And because carbon black is hydrophobic, it repels water, it gets forced into those exact tunnels.
Precisely. The carbon black particles cluster together, filling the capillary voids. What you are left with is a solid block of structural cement that contains a massive, continuous, fractal percolation network of conductive, wire-like carbon tunnels running entirely through it.
It creates an astronomically large internal surface area.
And surface area is the defining metric of a supercapacitor. Unlike a chemical battery that relies on moving ions, a supercapacitor stores energy through the Helmholtz double-layer capacitance effect.
Which means
It essentially stores static electrical charge right on the surface boundary between a conductive material and an electrolyte.
So you take this cured carbon black cement, soak in a standard liquid electrolyte like potassium chloride, and you've built a massive capacitor.
Out of concrete.
The numbers published by the MIT team are staggering. They calculate that a 45 cubic meter block of this doped concrete, which is roughly the size of a standard concrete foundation for a small family home, could store 10 kilowatt hours of electrical energy.
10 kilowatt hours is roughly 1/3 of the total daily electrical usage for an average American home.
Think about the implications of that. The cement industry is a massive climate villain, responsible for roughly 8% of all global CO2 emissions.
It's a huge carbon footprint.
But if the structural foundations of our homes, the retaining walls of our highways, and the pavement of our roads can suddenly double as an active energy storage grid,
It flips the script entirely. Imagine a highway paved with this supercapacitor concrete. It absorbs energy from adjacent solar panels during the day and then utilizes inductive charging coils embedded in the surface to wirelessly charge the electric vehicles driving over it at night.
the vehicle never have to stop to charge because the road is the battery.
Exactly.
And the literature hints at so many other avenues where the structure becomes the battery. The World Economic Forum listed structural battery composites in their top 10 emerging technologies. We are looking at carbon fiber composites, where the chassis of a car or the fuselage of an airplane stores the electricity to propel itself, drastically reducing the vehicle's weight.
Because right now, the battery is dead weight you have to carry around. If the wall of the plane is the battery, you save thousands of pounds.
Exactly. It all comes back to a deep, fundamental understanding of physics and chemistry. Once you understand the basic mechanics of electron transfer, potential energy, and thermodynamics, you stop seeing batteries as objects you buy in a store, and you start seeing the potential for energy storage in every single material around you.
Which is really the takeaway for aspiring engineers listening to this.
Absolutely. Which brings us perfectly to the end of our deep dive. I want to return to that brilliantly chaotic motto we started with. Electrical engineering is where almost anything can be a battery if you use it wrong enough.
It's so true.
We have seen today that energy isn't just a toxic paste wrapped in a plastic shell. Energy is chemistry, purposefully rusting an iron core to survive the dark doldrums.
Energy is motion, levitating carbon fiber flywheels in a vacuum against the rotation of the Earth to catapult fighter jets.
Energy is gravity, dropping millions of gallons of water down the toxic shafts of abandoned coal mines.
Energy is pressure, violently expanding cryogenic liquid air with the waste heat of a steel mill.
And now, it is the very structural cement of the walls around us.
I want to leave the listener with this final provocative thought to mull over. For the last century, human society has operated on a very rigid mental model of infrastructure.
How so?
We viewed energy as a discrete resource, something we extracted from the earth, burned, and then transported through our infrastructure. The infrastructure itself, the pipes, the roads, the transmission lines, the concrete, was just a passive, hollow vessel, a dead wire.
Right. The road doesn't do anything, it just lets the cars drive on it.
Exactly. But as we rethink the fundamental nature of energy storage, as we start mixing carbon black into the foundations of our homes and spinning flywheels and vacuums, what happens to the architecture of human society when the infrastructure itself becomes the energy?
It completely blurs the boundary between the places we live and the power that sustains them.
It really does.
Thank you for joining us on this deep dive. The next time you walk into a room and flip that binary light switch on the wall, I want you to look at the drywall. Look at the concrete floor beneath your feet. Feel the ambient heat in the air you are breathing, and just wonder, what else in this room could be a battery if I just used it wrong enough? We will catch you on the next one.